Okay, hi everyone. It's time for us to start the talk. Before I do the introduction, this is Yuri, by the way, for those of you who don't recognize the voice. Before I start the talk, I just want to remind folks that if you want to ask a question during the talk, please use the raise hand feature and I will call on you. Sam is going to stop at a couple of times throughout the talk and specifically ask for questions, but you can raise your hand throughout. You can also type your question if you would like me to read it rather than for you to say it yourself. There was one more reminder I wanted to make. The only other reminder that I wanted to make is that at some point I will ask you to unmute yourselves to clap. Please remember to unmute yourselves, otherwise Sam cannot hear you clap. Okay, so without further ado, let me do an introduction. So we're very excited today to have Sam Petti, who is visiting us from Harvard virtually. She's currently a postdoc at the NSF-Simons Center for Mathematical and Statistical Analysis of Biology at Harvard. She just received her PhD this past May from Georgia Tech, being advised by Santosh Vempala. She did her undergraduate not too far from here at Williams College in math, and so she's familiar with Western Massachusetts. So unfortunately, we couldn't have her physically here to come visit us today, but she already knows the beautiful foliage and all that business that we have here. She works on random graphs, probability, and algorithms. In particular, she focuses on building computational tools that help make sense of biological data, which is a really exciting application area of theory and something where I think that there's a lot of really cool stuff that can be done. So we're very excited to have her come visit us here as part of the Rising Stars series. And so today she's going to be talking about some of her recent work. Let's all unmute ourselves for the first time to clap and welcome Sam. Thanks, everyone. Take it away.
Thanks for the great introduction. So today I'll be talking about two disparate applications of independent set algorithms. First for the hard sphere model, and second for preparing biological sequence data for benchmarks. So I'll start by talking a little bit about my background. Then I'll talk about the hard sphere model. That part of the talk is joint work with Tyler Helmuth and Will Perkins. And then at the end, I'll talk about splitting sequence data into training and test sets, which is ongoing work during my postdoc with Sean Eddy. So my background, as Yuri said, is I had recently received my PhD in algorithms, combinatorics, and optimization from Georgia Tech, and I was in the math department there. And the themes of my research was graphs, probability, algorithms, and combinatorics. I'm now at a pivot point and I'm ready to try out applied things. So as a postdoc, I'm pivoting into the world of biology. So my goal broadly is to develop novel statistical inference and modeling methods to translate the recent explosion of DNA, RNA, and protein sequence data in order to say something about evolution, gene regulation, and the function of sequences. So broad strokes at first. So that's how you're going to end up seeing this talk. That's going to be two very different parts. So the first part is about the hard sphere model, and that's something I did in my last year of my PhD. And the second part is what I've been working on for the past few months since I started my postdoc. Fortunately, there is one common thread to both these parts of the talks that made it easier for me to make a title, which is that they have to do with independent set algorithms. So I'll just put that up front. You have a graph. An independent set is a set of vertices so that no pair of edges in the set is adjacent. So in these red circled dots or vertices are all form an independent set because there's no edges between them. And so this concept will pop up a couple times in this talk. Okay, so I'm going to start with the theory part of the talk and talk about the hard sphere model. And then the second part of the talk will be pretty much totally disjoint. So we'll start with the theory. Okay, so I'm going to tell you about the hard sphere model, but before I do, I need to tell you about sphere packings. So a sphere packing of a set lambda is a way of placing spheres into the set so the spheres don't overlap with each other and they don't go outside the set. So they're mutually non-overlapping and they're contained in the set. Sphere packings just in general are of interest for a variety of reasons. I'll just talk about a few. First is that sphere packings are really easy to define. So especially in 2 dimensions, that you don't need to have a mathematical background to sort of understand the notion of here's a bunch of spheres that aren't overlapping. In 3 dimensions, we see sphere packings at the grocery store with oranges stacked on top of each other. It's a really tangible problem. I'll be thinking about this in D dimensions, but if you prefer, you can just think in 2 or 3 dimensions. So despite being a really easy thing to think about, an easy concept, what's a sphere packing, we as mathematicians and physicists know remarkably little about sphere packings. In particular, we don't know what dense packings look like in high dimensions, and we don't even know what the correct order of magnitude of the density of the densest packing is. There's also all sorts of applications of sphere packings in coding theory. If you're trying to send some discrete set of messages and you want to encode them as vectors in space, you'd want those vectors to be far apart from each other so that if you send a message and it gets perturbed a little, you can still figure out what was trying to be sent. And last, the hard sphere model, which I'll define on the next slide, was one of the first applications of Markov chain Monte Carlo. So there's sort of a historical tradition of studying this problem in that community as well. So I'll be talking about the hard sphere model. And so the hard sphere model is a probability distribution over sphere packings. And it has 2 parameters. One is the set lambda. So all your spheres must be contained in the set lambda. And the second parameter also is very inconveniently called lambda, but lowercase lambda, and it's the fugacity parameter. So the fugacity parameter is going to control where the support of the distribution is. Is it going to favor packings with more spheres or fewer spheres? So in the hard sphere model, all packings with k centers or k spheres are equally likely. And then the higher this fugacity parameter is, the more that the probability distribution is supported on configurations, sphere packings with more spheres. So formally, we say the hard sphere model is a probability measure defined on conditioning a Poisson point process of intensity lambda on events that the points are at least pairwise distance 2r from each other. So that's saying if you drew the spheres, they wouldn't overlap. And second, they're all at least distance r from the boundary. And this is so that our spheres don't go outside of our set lambda. Okay, so that's the model. And we're interested in a particular property of the model, which is, does it have a phase transition or not? To define that, I'm going to need to introduce a notion of decay of correlations. So we say that a probability distribution on a set of spheres would have decay of correlations if fixing a sphere at a point x hardly influences whether there's a sphere at a faraway point y. So imagine we had 2 different distributions. This is a distribution over this sphere packing and this sphere packing. Say you pick each with probability half or something. And imagine over here you have a distribution over lots and lots of seemingly random sphere packings. In this model, we'd say there's no decay of correlations. If I tell you the packing that I sampled has a sphere down in this lower left corner, that's going to tell you that there's a sphere in this upper right corner. If I tell you there's not a sphere down here, it's going to tell you there's not a sphere up here. So knowing this sphere is going to tell you what's happening far away. In this example over here, we'd say there's decay of correlations. If I tell you there's a sphere exactly here at point X, it doesn't tell us whether or not there's going to be a sphere up here at point Y. So there's a conjectured phase transition for the hard sphere model. So before I talk about that, I want to draw an analogy to a physical phase transition, which is ice and water. So if you have H2O molecules and they're below 0 degrees Celsius, they're ice, and if they're above, they're water. There's no like in between ice water stage, either the molecules in ice or water, and there's that sudden point. And so the question is, in the hard sphere model, is there a similar phase transition? Is there a lambda? So remember, lambda is this fugacity parameter of how much the probability distribution favors packings with more spheres versus less spheres. Is there a particular point lambda where below that point, there is decay of correlations in the model and it looks very disordered? And then after that lambda, does it become a crystalline phase where there's no decay of correlations? For the experts in the audience, this might this might make more sense as thinking about this as the unique infinite volume Gibbs measure and the crystalline phase as the non-unique infinite volume Gibbs measure. So I won't go into formalizing that. You should just think, the question is, do we have a disordered phase and a crystalline phase? So this is the open question. Lambda C would be this critical value if there is this sharp phase transition. And if there's no phase transition, we would just say that this lambda critical is equal to infinity. It's known in one dimension that there's no phase transition in the hard sphere model. It's conjectured by physicists, although not completely agreed on by everyone, that there is not a phase transition in the sense I just defined for 2 dimensions, and that there should be a phase transition in 3 dimensions. So the goal of our work is to derive improved lower bounds on the critical fugacity by analyzing Markov chains. So we're not going to say anything about whether or not there is a phase transition. What we're going to say is if there is a phase transition, it happens after this higher point of lambda. So I'll start with some Markov chain basics. The first thing you should think about with Markov chains is Markov chains are a way of sampling from a probability distribution. So we want to sample from the hard sphere model. Here's one way to do it. You start with a configuration, some sphere packing, arbitrary sphere packing. And now in one step of the Markov chain, you're going to randomly change some small part of the configuration you have according to some rule. So in this step, maybe the random rule told us to remove this sphere. And so we end up with the same packing without that sphere. And we repeat following whatever this random rule that we carefully designed is. And eventually, if we do this t times, we want to think of this sphere packing as essentially a random sample from the hard sphere model. But of course, we don't have forever. We want this to happen for large t, but t that is polynomial in the size of the input. So formally, a Markov chain is rapidly mixing if the smallest value t for which this sample is close to the hard sphere model. And here I'm using total variation distance less than a constant to be our definition of close. We want that t to be polynomial in the size of the input. So this was vague. This is just general Markov chains. I'm going to now define what Markov chain, what is this rule? What is this Markov chain that allows us to actually sample from the hard sphere model? Our Markov chain is called single center dynamics, and we define them as follows. So this is, I'm telling you about the rule that goes from one configuration to the next. So the rule is, or I guess maybe more of a procedure than a rule, is first we choose a point x uniformly at random from our set lambda. So say I chose that x. And now we're going to flip a coin with probability fugacity over 1 plus fugacity. We're going to add a center at point x, only if doing so doesn't make the result not a sphere packing. So if this was our point x and our coin told us to try to add a point, we would add the sphere here, this point, because it doesn't overlap and doesn't go outside the box. So everything's good. If our coin flip came up the other way, with probability 1 over 1 plus lambda, we remove any centers within radius r of x. So if this was our x and our coin told us to try to remove, we would do nothing because there's no centers within radius r. For sake of another example, if this let's think about if this had been our point x that was chosen at random, with probability lambda over 1 plus lambda, we would try to add. So if we were trying to add a center here, we wouldn't, because if we were to add, we would end up with not a packing. So if we try to add, we do nothing. But now if we try to remove, we would remove this center here. So we'd end up with one less sphere. So these are the dynamics. And it's not too hard to show that the stationary distribution of this Markov chain is indeed the hard sphere model. And what that means is if you take enough samples, you let t tend to infinity, the distribution of the sample would look exactly like the hard sphere model. So our results is that the single center dynamics for the hard sphere model are rapidly mixing as long as our fugacity parameter lambda is strictly less than 2 to the minus d plus 1. And we then use this to achieve the best lower bound on the critical fugacity. So now the lower bound is that the critical fugacity is greater than or equal to 2 to the minus d plus 1, Or in other words, if there's a phase transition in the model, it must happen for some lambda greater than this value. So I'll quickly compare to previous results. There's methods called the cluster expansion or Poisson Boolean percolation, and our result is a higher lower bound. So we improved those lower bounds, both in d dimensions and in arbitrary dimensions. Or sorry, yeah, both in arbitrary d dimensions and in the specific case of 2 dimensions, which people have looked at a little bit more carefully, in part because you can get away with a little bit more using the 2D geometry, and in part just because people have been very interested in using MCMC methods to simulate the model, particularly for disks. So I've told you that we proved that single-center dynamics are fast mixing, and that we use this to improve the phase transition. So in spirit of having time for both parts of this talk, I'm just going to run through some of the proof ideas we use to show that single-center dynamics are fast mixing. And then I'll talk briefly about how our result that single-center dynamics are fast mixing translates into a statement about the improved lower bound. So first, I'll talk about our fast mixing proof. So the key ingredients are path coupling, which is a classic technique in the theoretical analysis of Markov chains. So path coupling is a way to prove that a Markov chain is rapidly mixing. And how it works is you define a metric D between pairs of configurations. So I have a sphere packing here and a sphere packing here, and my metric D tells me how far apart are these. And it's up to the user. I get to define what this metric is. I want to define this metric in a really particular way so that I can find a coupling of the Markov chain, so that if I have 2 instances, so 2 configurations, and I apply one move in the Markov chain to each, and then look at the distance they were before, and then I look at the distance after, that this expected change in distance is going to be negative as long as these 2 configurations were close to begin with. So that's the general technique that we used. The difficult part is defining our metric D in a smart way so that we can, and a coupling in a smart way so that this expected change in distance does decrease with each iteration of the Markov chain. For that's where the independent sets came in. So there's something called the hardcore model, which is sampling a random independent set on graphs. And Vigoda, I think in 2001, had a paper about how you can use Markov chains to sample independent sets from graphs according to this model. The hardcore model is really similar to the hard sphere model. It also has a property that all independent sets with the same size are equally as likely, and it has a fugacity parameter that makes the distribution center more on higher or larger independent sets or smaller independent sets, depending on the value. So we looked at Vigoda's work and saw the metric and the coupling that he used and adapted that to our continuous setting. So our problem isn't quite an independent set problem because we're looking at spheres overlapping, but it has a similar flavor. And in an independent set in a graph, you want a lot of things. And if you're trying to build an independent set, you want a lot of things, but the vertices, you don't want them, you can't choose 2 adjacent vertices. Likewise, if you're trying to build a dense sphere packing, you want a lot of centers, but they can't overlap. So very similar objectives, even though the continuity of the hard sphere model makes it a little different than the discrete case on the graph. Okay, and I'll end this section by talking about how our Markov chain has anything to do with the phase transition. So as I mentioned, the Markov chain is rapidly mixing. So we start at a configuration and then we sample from it a bunch of times. For large enough T, this sample really looks like it came from the hard sphere model. This implies a property called optimal temporal mixing. Optimal temporal mixing is the property that if you take 2 instances of Markov chains starting in different spots and run them enough, eventually the samples will look similar. Their distributions will look similar. And so this is a direct implication because the rapid mixing says that starting at a configuration, you end up towards the hard sphere model. And so this is just saying you start 2, they're both tending towards a hard sphere model. So they're tending towards each other. The harder step was showing that in our case, optimal temporal mixing implies strong spatial mixing. So we had to show this for the hard sphere model and single center dynamics. Strong spatial mixing you can think of as sort of like decay of correlations. It says that if you think of your set and you fix some spheres along the boundary of that set, and now you consider a subset within your set lambda, and you condition on these boundary points, and you look at the probability distribution within your small set lambda, and you compare that if you hadn't placed anything on the boundary and you're looking at the distribution on that set lambda, that those are very similar. So a short way of saying that is what's happening on the boundary doesn't really affect the probability distribution on a small area in the middle. So that you can sort of think of as decay of correlations. So we show that, and this implies the uniqueness of the infinite volume limit, which means that the phase transition has not happened. So we showed that single center dynamics of the Markov chain are rapidly mixing for lambda less than 2 to the minus d plus 1. And so then by this chain of implications, for lambda less than 2 to the minus d plus 1, the phase transition has not yet happened, and therefore the critical value is at least 2 to the minus d plus 1. Okay, I'll pause here for questions.
Cameron, can you go ahead and ask your question?
Yeah, I guess like a question I have is like, is the Markov chain, like, I guess you said the conjecture, you proved something like 0.5 or something in 2 dimensions, and the conjecture is actually like infinity or something. And is the looseness in like, do you know that it's Weir bound is tight for the actual Markov chain mixing, and it just doesn't translate tightly to the sphere packing, to the packing thing, or is it that the Markov chain might mix fast even with much higher fugacity?
All right, that was a great question. So I don't think that these bounds are tight for this Markov chain. I think you could probably show it's fast mixing for, or I believe that this Markov chain is fast mixing for higher lambda values. In our analysis, there's a lot of like worst case triangle inequality that it feels like rarely is the configuration actually going to be in this position, but we have to use this sort of worst case as our upper bound. So I don't have a good intuition for how far off, if there is a critical value that this Markov chain is versus where our analysis is.
Well, thanks.
Cameron, can you lower your hand so that next time you have a question, I recognize you? Laura, can you go ahead and ask your question? You have to unmute yourself. Or maybe.
Sorry, it's actually me, Peter, who's asking the question. Just out of curiosity, so there was apparently some, when you went from 2 dimensions to 3 dimensions, the conjecture about the transition point changed. I was wondering, there's this classic result for Markov chains and random walks, which talks about going from no recurrence to transients when you move from 2 to 3 dimensions. I was wondering if there were possibly any connections. Yeah, I guess it may have to do with degrees of freedom that might lead to some connection between those 2 phenomena.
Yeah, I hadn't thought directly about both those phenomena at the same time before. That's an interesting thought. I'm not sure I can speak directly to it, but I will say something about 2 dimensions, which, although it's conjecture that there's no phase transition in the sense that I said, there is a conjecture about a different form of phase transition where it's some sort of angular correlation. So if you know there's a sphere here and a sphere here, it increases the probability spheres on a rotation, like that there's going to be a sphere, like if you rotate a certain number of degrees. So I think it could be something in terms of the inherent geometry of the space, that the phase transition maybe in 3 and higher dimensions takes this form, but because there's something different about 2-dimensional geometry, that if there's this phase transition in 2 dimensions, many people think it will take this angular form. I mean, there could be both. There could be a sphere, a phase transition in the form I was talking about and an angular one, but some people think it's just the angular one. So yeah, there's something different about those geometries that I can't quite put my finger on.
Great, thank you.
Okay, I think that's all the questions we have. So Sam, go ahead.
Great. Great, thank you. Okay, so now we're totally switching gears. If I lost you completely, you can wake up and this is gonna be totally different. Although independent sets will appear once again. Okay, so let's see. I'm gonna talk about splitting biological sequence data into training and test sets for benchmarking. I'm gonna start by talking about a broad overview of how this process looks in like a typical machine learning application. So imagine you're trying to do some very important scientific task, like build a model that helps you figure out if your picture is of a muffin or a chihuahua. How this would work usually is you would split your data and you pick one set and call all these images your training data, and you get also, or split the other half or the other portion into the test set. And you would use this training data to parameterize some model here, which I'm representing by this cartoon. And you'd want this model to input a picture and output, this is a muffin or this is a chihuahua. So what this would look like if you want to sort of try to figure out how accurate your model is you would train it on the training data, and then you would put in each of the test images and then see, okay, did my model get it right? And then you would report that accuracy of, this is how accurate my model is. So it's really important that you are reporting your accuracy on data that you didn't train on, because this makes the accuracy you're reporting more representative of images your model hasn't seen. You want your model to be able to classify new images, so you should make sure when you're reporting accuracy, it's the accuracy on new images. So in a typical machine learning example, all you have to do is make sure your training set and your test set have different images. It's a little bit different in the context of biological sequence data. But before I get into that, I'm going to zoom out and talk a little bit about my big goal with biological sequences. So when I say biological sequences, you should think about DNA sequences that might code for a gene, or RNA sequences, or protein sequences. I'll focus here on protein sequences. So each protein is made of a sequence of amino acids. So you can think of these as just strings with an alphabet of 20 letters. So there's a database called PFAM, and it's a curated database of homologous protein families. So we say sequences are homologous if they're similar due to shared ancestry. So an example would be, we have a particular protein, mice also have that particular protein, and the way humans have their DNA encode for that protein might be a little different than the way the mice do. But we'd say those two sequences are homologous because they probably evolved from some common ancestor, and we can see this in both the sequences and the fact that they sort of have the same function in humans and mice. That would be like one example of a homologous pair. So this database has a bunch of families, and so you should think of each family as sequences from a bunch of different organisms that code for some their genes, or I guess we're thinking of them as proteins. So there are particular proteins that are found across different species, and they're very similar, and we think they evolved from a common ancestor at some point. So the big goal of my postdoc is to design models that can detect remote homologs. So here's my cartoon of it. We put in a protein sequence, and we want our model to output, yes, this is in the globin family, or no, this is not. So the current state of the art is hidden Markov models for this task, and I'm not going to get too into the details of that, but basically there's some way of inputting a sequence, aligning it to a hidden Markov model, and using this to output a guess, this is or is not a member of the family. And so hidden Markov models work pretty good, but we want to do something better. So in my postdoc, I'd like to redesign this model. But if I'm going to redesign this model, I'm going to need a way of saying, okay, my new model is better than the one that exists, or it's worse. I need to somehow have a good way of comparing it. So we need a smart way to divide our sequence data into training and test sets. So that's the current goal, split sequence data into sufficiently different training test sets to use to benchmark models. So there's a particular challenge of sequence data sets. In traditional ML, as I mentioned, you might independently assign data to test and training sequences. So you just say these guys are the test, or sorry, these guys are the training sequences and these guys are the test sequences. If we were to do this in the context of sequences, there'd be a lot of pairs of training test sequences that are really, really identical. I wrote here greater than 25% identical, but it's not uncommon to see hundreds of sequences that are like 90, 95% identical. And this is because the same sequence might look similar in a lot of different organisms. But we want, so if we were to do this, the accuracy we'd see reported on our test set wouldn't be a good indication of the ability of the model to classify sequences that are substantially different from those that it has already seen. We must carefully divide our data into test and training sets to avoid having very similar sequences in both. So to formalize this, our goal is as follows. We want our input to be some set of sequences and some similarity metric between the sequences. And our output is going to be a training and a test set so that no training test pair is greater than 25% identical and no pair of test sequences greater than 50% identical. So we've already talked about why we need the training and test sets to be sufficiently different so that we don't have our test set look really like what we trained on. And this extra restriction that no pair in the test set is greater than 50% identical, this is just so that if you're testing on a lot of sequences, you're really seeing like a breadth of what might happen if you put a new sequence into the model. If we put like 100 sequences that are all basically the same, it's not really giving us any additional information. So we're going to make sure our test set is different enough to give us some different information about how the model might behave on a variety of things that are related but don't look exactly identical. And you'll notice here with this arrow, a lot of the sequences had to disappear. In order to fulfill these requirements about the training and test set being different and the test set mutually being different, you're going to have to throw out some sequences. We don't want to throw out too many sequences, so we're going to require that both the training and test sets are large, and what large means is going to depend on the context. So the hidden Markov model that I briefly mentioned, you don't need too many sequences to train that, maybe 10. But if you want to start talking about using neural networks or POTS models for homology search, you're going to need hundreds and thousands of sequences. So you would need your training set to be that large. Okay, so I'm a graph person. And so first step when I saw this problem is let's make this into a problem about a graph. So here's an example. This is the Globin family, and this is the PF is just where it is in the PFAM database. And in that database, there's 74 sequences classified as the Globin family. And each sequence in this picture is represented as a vertex. And we draw an edge between a pair of vertices if the corresponding pair of sequences is greater than 25% similar. So I'm told that these are the alpha globins and these are the beta globins, and here are some other globins. So this is a graphical representation of the family. And to solve our splitting task, I'm going to introduce some graph theory concepts. The first is the independent set, which we talked about earlier, a set of vertices that mutually have no edges between them. And then I need to define a new notion to help us formalize what does it mean for the training and test set to be far apart. This helps us say the sequences we choose in the test set should be far apart. So I say that a disjoint set of vertices S and T form a bipartite independent pair if there is no edge between a vertex in S and a vertex in T. So in this example, you'll notice these 3 blue vertices, let's call them set S, and these 4 red vertices, we'll call them set T. They form a bipartite independent pair because if we look between any blue vertex and any red vertex, there's no edge. You'll notice there can be edges between blue vertices and there can be edges between red vertices. We don't really care what's happening there. We just need no edges between vertices that are blue and red. So the algorithms to divide, the algorithms I study to divide sequence families, which I'm thinking of as graphs, into training and test sets are all follow the same 4 steps. Step 1 is to construct a graph G1 in which each vertex is a sequence in the family, and edges are defined by the greater than 25% identity threshold. So that's exactly what I showed in the first slide, or not the first slide, the previous slide of the Globin family. The second step is to find sets S and T that form a bipartite independent pair in the graph G1. So our set S will be returned as the training set, and then the set T will choose our test set from it. So we'll then construct a graph G2 in which each vertex is a sequence in T, and edges are defined by now greater than 50% identity threshold. And then we will find an independent set U in G2, and we'll return U as the test set. So today I decided to only talk about two of the four algorithms that I've been studying for this task. The first I'll tell you about is the algorithm that is currently implemented in the biological software that people use for homology search. And then I'll tell you my favorite of the algorithms that I've come up with. So it's easy, or it's possible to recast the algorithm they were using into these four steps, as well as the algorithm I'll tell you about. So they all build a graph, find a bipartite independent set, build another graph, find an independent set. So the only things that change are step 2 and step 4, which is what is the algorithm we're using to find a bipartite independent pair, and what is the algorithm we're using to find an independent set. So when I describe the algorithms, I'm just going to be describing steps 2 and 4. So cluster is what I'm calling the original algorithm that's already implemented in the biology software, which they call this part of the software profmark. So here's how they do step 2, which is finding a bipartite independent set. So here's our Globin family from before. What they do is they look at the connected components. So there's 1, 2, 3, 4, plus I think 6 connected components in this graph. And they take the largest connected component and they say, great, that's our training set. And then they return that as a training set. And then they take everything else and they put that into the set T, which is the set of vertices from which we'll choose the independent set. So then you form an independent set U by selecting one vertex at random from each connected component of G2. So here's G2, it's all these vertices. You'll notice it has fewer edges. That's because the threshold for where there's an edge got increased to 50%. So here's our graph G2, and we'll take one vertex from each connected component at random, and this would be our test set U. Okay, so now this is the algorithm. I'd say on the whole, it works okay. It's able to split some families, but it really struggles to split other families. And in particular, it struggles on large families. And so I'm going to give some synthetic examples to give some intuition of why this algorithm isn't great overall. So first, imagine you had this graph. Imagine your protein family got encoded as this graph. Visually, if I were to want to do this just by hand, I'd say, okay, let's make these the training set, and then let's investigate this cluster here and see if we can find a test set within it. But if you're the cluster algorithm, you're like, there's only one connected component. You circle all these and then put that into the training set, and then you'd be like, oh, there's no test sequences left, and you're done with this example. You can't use it because it has no test sequences. So you run into trouble when there's only one connected component, and this is particularly more likely when you have lots and lots of sequences, that everything eventually will be connected through one component, and this type of algorithm isn't going to help you split your data. The other issue comes in the second step, in that you're not choosing a maximal independent set. So the rule is for each connected component in G2, you're just going to pick one vertex. Imagine this was your one of your connected components in G2. What would happen is you just pick one vertex and then say, okay, that's the contribution from this connected component into the test set. But you could imagine just looking at this, okay, if I wanted to maximize my test set and it has to be an independent set, I would just throw out this middle vertex and then put all these vertices in my test set. And the algorithm doesn't do that, it just picks one. So there's room for improvement there. Okay. So now I'll talk about an algorithm I developed, which I just called the blue algorithm. And and how it works to find an independent set in a bipartite independent pair. I'm going to start, for the sake of simplicity, by describing the independent set algorithm. The independent set algorithm is a pretty direct adaptation of an algorithm due to Metiver et al. From 2010. And we adapted it first for the independent set part, and then for this bipartite independent set, but I'm talking about the independent set part. So think about step 4. We're just trying to find an independent set, and we've already found our training set. Now we have this big set, and we need to choose our test set from it. So here's how the algorithm works. I actually implemented it quite differently, which I'll talk about in a little bit. But here's the most intuitive way of thinking about the algorithm. So you're going to build an independent set U over multiple steps. So you're going to start with U being the empty set. No vertices have been added to the independent set yet. And then while the graph is not empty, you're going to iteratively add vertices to the independent set and remove vertices from the graph. So this is a multi-round process. In the at the start of each round, for every vertex that's in the graph, you'll give it a label with a uniform random value in between 0 and 1. So here we have all our vertices, and we put those random values on. Next, you're going to place the vertices in a random order. So here in blue, I've ordered them randomly. And now we iterate through the vertices in the random order and do the following. So we start with vertex 1. And if this vertex has a lower label than all of its neighbors, it gets to go into the independent set. So 0.5 is not lower than 0.3, so 1 does not get to go in the independent set, and we move on to the second vertex. The second vertex is labeled 0.1. This is lower than 0.4, 0.6, and 0.3, so vertex 2 does get to go in the independent set. When this happens, all of its neighbors are deleted from the graph. And this makes sense because once we've added vertex 2 to our independent set, we know that none of its neighbors are going to be allowed to go into the independent set. So now we move on to vertex 3. Oh, it's not in the graph anymore. We skip it. Now we're at vertex 4. And we see that it does not have a smaller label than all of its neighbors. So we don't add it. Vertex 5 and vertex 6 are no longer in the graph. So our next is 7. 7 does not have a smaller label, so we move on. Vertex 8 has no neighbors, so it has the smallest label. It goes in the independent set. Now we've iterated through all the vertices. We're done with this round. We repeat, assign a random order and a random label, and do the same process. 1 is going to go in the independent set, and then 3 will also end up in the independent set. So this is how the algorithm works over multiple rounds to build up an independent set. So I've explained it in this way, as thinking about it as I have this graph here, and I'm just going to perform this algorithm on the graph. The way I implemented it in the actual code was much more fun. It doesn't have the graph pre-computed, and instead it only computes whether or not there's an edge when it needs to, but I'm not going to get too much into that. So let's see. I think I'm going to skip how this algorithm works in step 2, other than to just say some broad strokes about it. So step 2, we're trying to build this bipartite independent pair instead of an independent set. So it's a very similar thing where in each round, I like to think of the vertices as running for the independent set. So in each round, now each vertex is going to be a candidate that's going to try to get in the S set or try to get into the T set. And it's only going to get into the set if it's lower, it has a lower label than its vertices, than its adjacent vertices that are running for the opposite set. So it's a very similar idea. I will point out one key feature, which is it's the algorithm that's an adaptation of the independent set algorithm I just showed you. It's going to produce a set S and T that are a bipartite independent pair. But what it will do is whichever side happens to be bigger, it will return that as the training set. This is because we want our training set to be larger than our test set, just because the model has might have a lot of parameters, and we want our training set to be big. So that's one way the algorithm does it. Okay, so I've already talked a little bit about why cluster doesn't work. I'm going to talk a bit about why blue at least in theory, should work a lot better than cluster, and it does, which I'll show you next. So the first is the probability of being included in the independent set is inversely proportional to degree. So let's just think about the independent set 4, and why does it do step 4 better? A similar type of argument will explain why it does step 2 better. So say you're trying to build a really big independent set on your graph. You wouldn't want to put a vertex with really high degree in the independent set, because if you put that high degree vertex in, now all of its neighbors are disqualified from being in the independent set. So if you're trying to build a big independent set, the best way to go about it is try intuitively to put lower degree vertices in. So the algorithm implicitly does this by saying if a vertex has a lower label than all of its neighbors, it goes in the independent set. Well, if you have a lot of neighbors, it's a lot less likely that you're the lowest. So if you have like 100 neighbors, probability you're the lowest of all your neighbors is quite small, as opposed to if you only have a few neighbors. The other advantage of the blue algorithm is that it's a random algorithm. So in the cluster algorithm, you'll end up with the same training set every single time, right? That largest connected component, no randomness there. And then you'll end up with a test set that's the same size every time, because you have a fixed number of connected components. It's random in terms of who you take from which connected component, but you'll hit the same number. So there's no variation. In blue, in contrast, if you run this algorithm multiple times, you'll have different results. The vertices you add first to the independent sets might have a really strong influence. So if you just run it a few times and you have different first vertices, you might end up with totally different splits. And so blue really leverages this. We can run it multiple times, and maybe many times it just gives us nothing, but 1 in 10 times it gives us a great split. So that's part of why it will be successful. Okay, so before I quantify what I mean by blue is successful, I'm going to pause here if anyone has questions about the algorithms.
So if anybody has a question, oh, I see Brianna. Oh, no, Brianna put her in down. Cameron, can you ask your question?
So is the whole goal, like, let's say we just care about let's say you've already split S&T, you've already split training and test, and then you're trying to just get an independent set on, I forget which side, the test side, I guess.
Yes.
Is your whole goal basically to have a heuristic for maximum independent set? Like, is that the end goal? Like, the bigger that is, the better? Like, the bigger the independent set you find on that test side, the better? Or is that not quite right?
No, that's right. I think
Okay.
more globally, we think of the goal as maximizing the product of the test and training side. But we do kind of like to see the training side be bigger, which is why we do that little, okay, we'll just make the bigger one the training set.
Okay.
Rule.
And then like my other question, which my first question validates this, but you were talking like earlier in the talk about these algorithms for like sampling random independent sets. And like, I guess this algorithm is probably not quite doing that, where I don't really know, but could you run like a Markov chain to just keep sampling random independent sets until you get one that's like good, that is big enough or something?
Yeah, I haven't tried that. So the question was like, why not just start with some independent set and run a Markov chain and see if you get something better over time? Yeah, I think you could do that. I think it would probably take a little bit more time to get far from something that you started with. So the sort of one shot, is this good enough? We'll just randomly choose this one, and then if it's big enough, we'll call it, as opposed to looking for the optimal. It's like a time maximal, or a time versus size trade-off. With more time, maybe with a Markov chain, we could end up with a larger set. I'm not sure.
Right. Cool. Thanks.
Peter, I assume. Peter, you're muted.
Sorry. Sorry, my assistant was slow to unmute me. So our graph database expert Marco Serafini isn't here today, so I'll try and ask his question, which is that I don't know whether performance considerations are important in this process of finding test and training sets. I'm just wondering whether you've looked into the effect of different representations of the graph have on the speed at which you're able to do these computations.
All right, that's a good question. So about representing the graph. So actually, the way I first implemented this is I took the data and then computed all the pairwise distances and said, okay, this is my graph, and it was input as I think it was whatever Python Network X does. So I think it was an adjacency list. But then I quickly realized it's not actually, we don't actually need the graph for these algorithms. So in the way that I described it to you in the pseudocode, I was like, look at all your neighbors. There you're going to need the graph if you're iterating through neighbors. But the implementation actually ended up being quite different. So we actually never store any graph information. We put the vertices in particular orders, and then we iterate through and we're like, okay, we're gonna have to test to see if there is an edge here, and then we compute, is there an edge or not? And then our algorithm progresses based on whether or not there's an edge, and we don't even store that information because we'll never need it again. That's actually true within each step. So within step 2, we never query what is this edge here more than once within step 2. And then also we never query it more than once within step 4. I thought a little bit about storing it in between the steps, but I think by the time you have to allocate memory to store it, it just wouldn't be worth it, especially when we're talking about families with hundreds of thousands of sequences.
Okay, this is even if you're running the algorithm multiple times, as you said, to get some variety.
Yeah, so we just don't store it. We just start from scratch each time. I think if you were to want to run it multiple times, a lot, and you might want to look into storing it, but for our purposes, it's just fast enough to not store it, so we don't.
Okay, thank you.
Okay, that looks at all the questions we have right now, so we should go forward.
Great. Okay, so I'm going to tell you a little bit about how this algorithm works on the PFAM database. So a bit about PFAM is that it has 18,259 protein families, and of those, 12,340 families have at least 12 sequences. So we're going to say that the splitting algorithm is successful if it produces at least 10 training and at least 2 test sequences. So I'll just quickly say that's all I'm going to show you, this particular database, and these are called like the seed alignments. These are smaller alignments. I mean, you can see the distribution of the sizes here. There's also a full database, which has much larger alignments, which I also study, and some of the sort of don't store the graph because it's big is not because of this data, it's because of this other data that I'm not going to talk about. Okay, so we see that of these different algorithms, so cluster, that's the algorithm that was there, of these 12,340 families, it's able to successfully split 19%. If we run the blue algorithm once, it's able to successfully split it 34% of the time. And if we run the algorithm 40 times and then stop whenever we have a success, then we get 60% of the database, or 60% of the families in the database. So we can also look at what types of graphs is this algorithm doing well on versus not. So here in this plot, each point in the scatter plot corresponds to some family in the database. So there's like 12,000-ish points. And the x coordinate of each point is the number of sequences in the family, and the y coordinate of the point is the average connectivity. So on average, for an average sequence, what fraction of other sequences is it connected to? So this up here, high on the y-axis means very dense and very similar sequences. And then high on the x-axis means many sequences of the family. So you can see cluster, it really struggles, especially when there's more connectivity in the family, right? Because then you're probably maybe just one component and then the algorithm will fail. Blue 1 does better. You can see that it's starting to get more of these more connected graphs. And blue 40 does even better. So you can see here that the algorithm is really only failing on families that are incredibly dense, that there might not even be a set of training and test sequences, we don't know, or small families, right? If you have to produce a training set of size 10 and a test set of size 2 and you only have 15 sequences, that might make it really hard to maneuver them in a way where you're not throwing out too many and still getting this adequate split. So it was, I guess, a threefold improvement over the current algorithm. So the whole point of this algorithm, or the whole point of these splitting algorithms, is that we want to be able to have a training set and a test set and evaluate how different models or different models of homology search are doing, how accurate are they. So we first looked at this particular method called HMMSearch, which is a hidden Markov-based method that I'm not going to get into the details of. And we said, okay, if we split according to cluster and we split according to blue, how accurate is this exact same algorithm? And it looks very different. So these are the raw curves. This is the mean false positive search on the x-axis, the true positive fraction on the y-axis. You should just focus on the blue and the green right now. Those are the two algorithms I told you about. The other algorithms I just kept up here to show that it does vary depending on what algorithm you use. So if you were to split your data according to the cluster green algorithm, and then you were to ask how good at identifying homologs is HMMSearch, you'd say, okay, it's 75 to 85%. But if you were to use the blue algorithm, you'd say, oh, well, it's 90 to 95% accurate. That's a huge difference. To be clear, it's the same exact method. The only thing that changed was how we split our data. And both ways of splitting the data, we had the same requirement on differences between training and test sets. So what we see is that different splitting methods. So most notably blue and cluster, because those are the ones I told you about today. But to some extent, these other two random ones, random or independent selection and cobalt, are also different from each other. So what this really says is that you can't really come up with an absolute number for the accuracy of a homology search algorithm, because that number is going to depend not on the homology search algorithm necessarily as much as how you split this data into training and test sequences. So what do we do from here? Well, we can hope that, okay, clearly our reported accuracy is very different depending on how we split the data, but hopefully the relative accuracy is maintained if instead of using HH-search, we use other methods. And fortunately, we do see that. So here are 5 different homology search techniques. And here is the benchmark raw curves that you'd see from the different splits. So if we use the cluster algorithm and then we, for our benchmark versus blue 1 versus blue 40, we see all of these roughly the same shape, roughly the same order. It seems like HMMSearch is always at the top. And I mean, they're not exactly the same, but roughly they're the same. So it's good that the relative rankings of the algorithms are maintained across the splitting algorithms. So with that, I'll leave it open for questions.
Thank you, Sam. That was great. Let me start with a question. So normally, when you think of splitting splitting data into a training set and a testing set, the implication of evaluating the testing set is if you get, let's say, precision of 80%, then you could say that given a random sample, I guess uniformly random from the space from the same distribution as your testing set, this is the probability that your thing will identify it correctly, your classifier will identify it. So now you've biased how you're selecting your testing set. So now what you're saying is if you select a different enough homolog, right? So where different enough is sort of, well, it's defined kind of by the algorithm. So what does that really mean in practice? If for a given protein, if, I don't know, 95% you said happens sometimes of the genes are identical between organisms, then it's just an easy problem to identify whether those belong to the family or not. So, but your precision now doesn't measure that. Your precision sort of artificially deflated to overrepresent the hard to identify cases. So how do you go back from it? So I guess well, I'm not sure what my question is, more of a comment and sort of how do you reconcile the fact that you're now not measuring the normal precision thing, and perhaps it is more difficult in papers to describe why in related work algorithms seem to perform much better than yours. And then the corollary of that is that you could actually keep, report precision on a randomly selected testing set. And sort of show that it's actually much higher given a random thing, but given our bias in selecting the testing set, here's what the number is. Those are a bunch of incoherent thoughts. Do you have any thoughts on my thoughts?
I do have thoughts on your thoughts. I like the way you framed it as thinking about the training in the test set as, or in traditional ML, you want the training in the test set to, you can think of them as being drawn from the same distribution, right? Like if your goal is to distinguish cats from dogs, any cat and dog in your training set should look like there's some distribution over images in this world of cats and dogs in your training set should look like the test set. I think it's a different question you want to ask when you're for homology search, because your goal isn't to find homologs that look like the ones you've already found, but you actually want to find homologs that look totally different. So if you want to actually think about the model, here's another way to actually think about the homolog model. Like there is some true distribution over sequences that are the same homolog. And we've actually only observed a very small fraction of them, because there are certain organisms that biologists study more. And so the only data, like there is this true distribution, but we only see this tiny subset that science has discovered. And so now we want to figure out the whole big distribution, but we've only seen a small part. So what we should do is we should see how good is our model at seeing part of the distribution that hasn't seen. And that's why you should think about taking your training data to be a subset that's far away from your test data within this tiny patch of this huge distribution that you don't see. So it's a question of what you want.
Mm-hmm.
Yeah.
That's reasonable. And I think sort of another counterpoint there is that your space of all possible sequences that you might be asked this question about is huge, and almost none of them are actually homologs, right? There's lots of from other. And so if you really wanted to sample honestly from this distribution, then almost everything should be a negative. And so measuring precision would be very difficult there. And so you need to bias it. Okay, so we're actually over time. Are there any pressing questions, or should we thank Sam? Pressing questions going once, twice? Let's all clap one more time and thank Sam.